Let's talk about NPSH. I know it sounds horrible, but it's a lot easier than it sounds. NPSH means net positive suction head. We already know about suction head, that's the head of the suction. Now net, there's two components to net. The head of the suction is up to now has always been independent of the atmospheric pressure. In other words, if I got 0 psi, I also got 0 feet of head. But in terms of NPSH, we have to consider the atmospheric pressure. So we're going to add that to the suction head. Now, why the atmospheric pressure? Because you can imagine if your pump is located in Mexico, that's 8,000 feet in the air, the atmospheric air pressure is actually a lot less than it is here. I mean, if you're here, close to sea level, it's 14.7 psi. In Mexico, I think it's around 10 or 11 psi. If you're at the top of Mount Everest, if you're a climber, the atmospheric pressure at the top of Mount Everest is 3 psi. So you can see, depending on where you are, there's a lot less atmospheric pressure pushing on the surface of your suction tank to help the pump out. And that's why, if you haven't taken that into account, some pumps may not operate as well in high locations as others. So to the suction head, we need to add the atmospheric pressure. Then we need to subtract it from something called the vapor pressure. This is something really interesting. We're going to see a little video about vapor pressure. There's two ways to make a liquid boil. You can make a liquid boil by just boiling it on a stove. You put water into a pan and you boil it, right? And you'll evaporate it. Or you can do something else, which is put water in a sealed container and lower the pressure in the container. So we can actually get water to boil at a low temperature, and you'll see a video about this. It's quite fascinating. So depending on the temperature of your liquid, it'll have a propensity to boil off quicker or easier if you lower the pressure than if it's colder, a colder liquid. So that's why we have to remove this element, this number called vapor pressure, it's going to be vapor pressure head, from the suction head. Usually this number is very small, but if your liquids are hot, this number will be large, and that's why it's important. So I'm going to get back to NPSH a little later, and now we're going to look at this video that shows how we can boil liquid water at low pressures. This is an experiment to demonstrate the effect of vapor pressure. We know that we can make water boil on a stove, for example, at 200 degrees Fahrenheit if we add heat. We can also make water boil at lower temperature by using low pressure. This small reservoir is connected to a low pressure source, and I have water in here at room temperature. The low pressure source is a venturi, which is connected to this tap. The tap will provide the pressure required to make the venturi work and provide low pressure into the small reservoir. So I'll just turn the water on and we'll start the vacuum going. You can see here a vacuum gauge. The vacuum gauge is in inches of mercury and indicates how much vacuum is now in the reservoir. We need to get down to minus 28 inches of mercury to get good boiling for this water at room temperature. So we're down to about minus 20 right now. First thing that happens is all the air that's in the reservoir will be pulled out of the water and pulled out through the vacuum hose. So we're starting to see all these little air bubbles form and coming out of the water. And now as the pressure drops further, now we're getting vapor bubbles, or actual water vapor bubbles occurring due to the low pressure. So we're down to approximately minus 26, going a little bit further, and we're starting to get really good boiling here, or vaporization of the water. I think you can see that this water is definitely boiling. Okay, so now I'm going to shut this off and show you that this water is actually quite cool. free my hand in here. It's nice and cool. And there you have it. Water boiling at low pressure. Pretty interesting watching water boil at low temperature, isn't it? So another way to look at this, if we look at this graph here, on the y-axis we have pressure, and on x we have temperature. And there's this line here called the vaporization line. So if I go horizontal across, that means I stay at the same pressure, right? So that's exactly like boiling water on a stove. I've got my water, pressure around the environment doesn't change. The more I raise the heat, eventually I'll reach that vaporization line, and then it'll boil. But I can do the same thing if I keep the temperature constant and go down the y-axis and now change the pressure. So I start off at atmospheric pressure and I reduce the pressure. At one point, bang, I'm going to hit the vaporization line again. So I could hit that line and using both those methods, lowering temperature and lowering pressure, and that's often what happens in industry. The water's not quite all that hot, but it's hot enough that a small drop in pressure will make it boil. Now, how do we put all this together? So we know that we have NPSH, A for available, that's what that means. So it's what's available to me as a user, is going to be equal to the suction head. I'm going to subtract the friction head and that bit of line. Usually that's very small, but if I have very high flow, small line, that might be a significant factor. Then I'm subtracting the vapor pressure of my liquid. I'll have to find that number. Where? Guess what? On the internet. If you know what liquid you have and temperature, you'll get that number. And then we add the local atmospheric pressure head in our environment. So at sea level, it's about 14.7 psi. In terms of head, that's about 32, 33 feet of water. So this will give you a number of what's available to you. The manufacturer doesn't know what's available to you, but he's going to test his pumps in such a way to find out how much NPSH do I need to run these pumps at a given flow rate. So he's going to come up with that number and he's going to provide that to you in another set of curves. We won't get into that, but that's a number that you have to be sure that your available is above his required. So your NPSH available, NPSHA, must be higher than his NPSH required. This brings us to an interesting topic called cavitation. We've done all the groundwork for this, so this will be easy sailing. So cavitation is a phenomenon that occurs when pressure drops below the vapor pressure of a liquid. So it occurs in pumps at the pump suction. It occurs in valves and any other place where we have a sharp drop in pressure and the liquid is at a certain temperature that this drop in pressure will cause vaporization. So I have a chart here showing how the path of the liquid into the pump, how it changes in pressure. So as we come into the suction, we get a drop, immediate drop right at the suction at the eye of the impeller because the eye is a little bit smaller than the pipe that leads up to it. So as we know, if we transfer into something smaller from a larger pipe to a smaller pipe, pressure will drop. So that's why we're beginning to see this pressure drop. And as we go through inside the eye and turn around up to the impeller, we have further pressure drop. So if the flow rate is such that it's high enough that we get this high pressure drop, combined with the fact that we may have a slightly hot liquid or whatever, we could have a pressure drop high enough that the liquid will vaporize, as we've seen earlier. So in the pump, what happens when liquid vaporizes is that we're at the low point of the pressure drop, and then we start to get onto the impeller, and now we're getting positive pressure created by the impeller. We have vapor bubbles created by the low pressure drop. All of a sudden we get very fast, high pressure, so this collapses this bubble, and this shock, this little shock of each bubble creates a shock wave that will pit the impeller after time and cause some serious wear, as you're going to see in this picture. So the wear will go over time, but you know, it's not instantaneous, and it'll take several days, weeks, perhaps months for the metal to degrade. And it depends, of course, on the type of metal. Bronze is softer than stainless steel. and there are other metals that are available that will, you may have the cavitation, but won't have the serious results that we'll see in this picture. So here's the sound of cavitation. You can hear it's a rather distinctive sound. It's got this, it's a little like recording rocks, and it's quite distinctive. It's really good anytime you hear this, you know you have cavitation. You can also hear the sound of valves where the pressure drop is too severe, and the valve is not properly located as we discussed, or the valve is not of the right type, and we'll have the same phenomenon occur there also. So here's what a damaged impeller can look like with cavitation. You can see how eroded it is, and obviously the pump's performance will deteriorate over time because of this.